but you'll get to learn about aircraft, right? You'll be fine. Don't worry about it. You will definitely be fine. Okay, what time is it? You guys are junior students, right? Okay. Because we were trying to nominate people for the best senior awards. Some of your names came up. I told them these people are not seniors yet. Pardon me? Yeah, some of your names. Let me put this here. We finished chapter 4, right?
Yeah, so that one problem, the flow from laminar to turbulent at v infinite equals 10 meters per second and 40 meters per second.
Didn't we finish that? I thought we finished that, right? So I'm gonna assume we have finished that. We're gonna continue with aerodynamic shapes. Okay, so we are live on YouTube and Blackboard. For people who have joined the Blackboard session, keep in mind that we are eventually going to move away from Blackboard and going to only stick to the YouTube. And I think recording on YouTube is a better way to go because it is easier to have access to the recordings. It is easier to edit them. I mean, on Blackboard, there's no way for you to edit them. You have to remove the whole thing. And yeah, someone's testing. Yeah, I see your comments, Steven. So your testing was successful, I guess. And what time is that? 10:06. Yeah. So we were, I think we were in the middle of solving an example problem. But hopefully you got the hang of the problem. You know how to finalize the solution, continue solving the problem yourself. So I'm going to leave it to you to finish that problem. Okay? And you are going to start chapter 5 today. But your homework, which is completely based on chapter 4, essentially the review of aerodynamics, is already posted. It was posted last night, but it will be due next Tuesday, so you don't have to submit it on Monday. Next Tuesday before the class. So when you come in, just submit a hard copy. And if you are an online student, I will create a portal. Let's do this because we don't have that many students in class. I'm gonna create an assignment portal on Blackboard, and all of you just submit it on Blackboard. Okay? Is there any questions? No? Okay, I don't have my notes on the chapter 4 or that problem, so I have to go get them. So let's do it next Thursday, okay? But I don't have the problem with me, and I also don't have the final numbers as well. Yeah, we're gonna revisit this problem on Thursday, and I will give you the final correct numbers for your solutions. Okay, let's just start chapter 5. Chapter 5, we are mainly talking about aerodynamic shapes. aerodynamic forces, and how to calculate aerodynamic forces for different shapes, how to relate these two. Some parts of this material I think you should have seen in your aerodynamics. So I'm just gonna go over them quickly, but if you think you haven't seen this material in your aerodynamics, or if you don't remember them, just stop me, ask questions, and we'll try to go in more detail. But in general, the first thing you want to talk about is the nomenclature we use in aerodynamics, right? An airfoil, let me ask you actually, what is an airfoil?
Isn't it typically a structure that applies lift on an aircraft?
A structure that applies lift on an aircraft. But what does this? What does differentiate between an airfoil and a wing? Okay, exactly. So an airfoil is a cross section of the wing. Right? This essentially means that an airfoil is a two-dimensional object that we do the aerodynamic analysis on. Okay, what are the different parts of an airfoil? Let's say this is a schematics of an airfoil. We have the leading edge. We have the trailing edge. So leading edge is the first place the flow hits at zero angle of attack, and trailing edge is the last place the flow leaves the plane. The distance between the two, the smallest distance between the two, is called the chord length, or chord in general. And this is a value we deal with a lot. We usually identify airfoils based on their chord length and some other numbers, right? The distance from top to the bottom of the airfoil is called the thickness. And we actually, for an airfoil that is cambered, you're going to have a mean camber line. So for this airfoil, the mean camber line doesn't really, it does look a little weird, but think of an airfoil like this, right? The mean camber line is a line that has the exact same distance from the top and the bottom of the airfoil. And this one, the chord length is this, okay? Chord is always the shortest distance. It can go from the leading edge to trailing edge. Okay. We usually call the angle the flow direction makes with the chord length, the angle of attack. And that's it for the basic names that we have to be familiar with. But let's move on to forces. When it comes to forces, we have two different perspectives to characterize the force. First of all, there will always be, let me do it here. We will always have a resultant force, right? That is essentially, as we have talked about it, is there because of the pressure distribution around the wing, around the airfoil, or whatever you're dealing with, as well as the shear, right? So a combination of these pressures and shears are, we can combine them all into one resultant force and one moment. Okay. When it comes to these forces, we can have two different perspectives. We can find the component of these forces by treating your core as one of your axes. So coordinate system will be this, X, Y, okay? If you do so, we're gonna get a normal force and axial force. The other perspective, which is a more popular perspective, is to use the direction of the flow as the guiding direction for the XY, whatever that is, for finding the component of the force. Based on this, the force that is normal to the direction of the flow is going to be called lift, and the force that is normal, tangential to the direction of the flow is going to be called drag. We have seen these two perspectives in your fluid mechanics, hopefully, or in your aerodynamics, and you're gonna we don't have anyone in class who is taking aerodynamics right now, right? It was only Vic who is not here. We can actually find the relationship between these two perspectives using the angle of attack. So your lift is going to be equals to n cosine of alpha minus a sine of alpha, where alpha is your angle of attack. And your drag is going to be n sine of alpha minus a cosine of alpha. Okay. Is there any questions so far? These are just repetitions of what we have seen before. Just a reminder, just to refresh your memories. And then we're going to move on to the force coefficients based on this. How did we define a force coefficient in general? Like the definition of a force coefficient. It was a dimensionless parameter, right? In general, how did we define a force coefficient? It is force multiplied or divided by whatever, right? Do you remember that? Okay, what was it?
Was it force over unit area?
Force over unit area. Okay. Let me ask you this: Did you do dimensional analysis in your aerodynamics, like Buckingham Pi theorem? You did not. Did you do dimensional analysis in your aerodynamics, like Buckingham Pi theorem? Okay, so Steven is telling me that you have not done that, and okay, so it is important. Dimensional analysis, we have a very small section on Buckingham-Pi theorem and dimensional analysis in this chapter, but it is definitely not the focus on the course and we are not going to go over it. But so let me ask you this: why do we have dimensionless? We are familiar with dimensionless parameters, though, right? If coefficient, drag coefficient. Why do we have those? See, exactly. So to be able to test something in a wind tunnel, and we have discussed this in this class as well, to be able to test something in a wind tunnel and then apply the findings to a bigger scaled model of whatever you are dealing with, right? If we didn't use the dimensionless parameters, then the dimensions, the units, would have played an important role. Like the length would change your force, right? The total force, right? Because you're going to get a more area that is going to be covered by your pressure and shear. Does that make sense? So we have the dimensional parameters for this specific reason. And then in aerodynamics, the force coefficients are going to be important. We usually use C as like it stands for coefficient. Then I'm just going to give you a general definition. C of any force coefficient, right? CF is usually friction coefficient, but that's a small f. So this is general definition. Is going to be, we are looking for a dimensionless parameter, okay? So, and it has to be related to your specific force. So we have to have force in this formulation, no matter what. And then we have to remove the dimension of the force by normalizing this force using another parameter, right? If you had done any dimensional analysis, you would have known that we usually take a parameter here to normalize your force, to non-dimensionalize the force, right? That is that doesn't change with your flow. That's like a characteristics of the flow. Like if you were non-dimensionalizing velocity, you would have used free stream velocity. Free stream velocity is something you define, right? That doesn't change based on the location or anything, angle of attack or whatever, right? Okay, so what do we have that has the same dimensions as the force and is something that is a property of the fluid, right? That far stream, or something that you don't really change after you have set up your problem, right? So what do we have? We have pressure infinity, we have velocity, right? These are the free stream parameters. Your span area doesn't change as well after you have set the problem, doesn't change. What else doesn't change? Like the pressure distribution on the wing change based on location. Velocity on the wing change based on the location. The same is true for shear, angle of attack, you can like move, right? So these are essentially the three parameters that are not going to change. Like we can calculate Mach number and the free stream Mach number, all of those things based on this, right? So if you recall, we had a parameter called dynamic pressure that was related to this. So dynamic pressure itself is also a function of like a free stream function that is by definition a general parameter that we set, right? Also true span area. So what will happen if you multiply Q infinity by S? No, if you multiply this, what is the units for Q? This is it. This is a pressure, right? It's force per unit area. What will happen if you multiply a force per unit area by an area? Force. So do we have what we need? So we are normalizing whatever force we have with something that is independent of the location, the nature of that force for that specific problem. Does that make any sense? So it is important. Whenever you didn't remember the formula for any of your force coefficients, you come back to this definition and you do the calculation. So based on this, your lift coefficient is going to be lift divided by Q infinity span area. Your drag coefficient is going to be drag by Q infinity span area. Your like normal force coefficient is going to be normal force divided by Q infinity span, and so on and so forth. I would let me do this actually. I'm going to give you a bonus point to if you give me a summary of section 5.3. Write a summary for me, like a one or 2 page summary. Section 5.3 of the book. Is there anyone who doesn't have access to the book? Okay, so a bonus point because that's where the dimensional analysis is done, and we are not gonna go over this in this class. Give me a summary of 5.3. Dimensional analysis and Buckingham-Pi theorem. I don't think they have used the name Buckingham-Pi theorem. And if you, let me actually write the theorem's name. Buckingham-Pi theorem. So there was this guy, Buckingham, who came up with a method to calculate dimensionless parameters and called those general dimensions parameters pi's. Pi as in the Greek letter pi, right? Not an apple pie. Okay, is any questions so far? So, okay, so based on this definition, what would be the moment coefficient? C of M. Anyone?
Yes, unit S is on the top.
Okay, but the units of this is newtons, right? So on the top, we're gonna have the moment, right? Because moment coefficient. What is the unit of a moment? Newton meters. So if you divide these two, you're gonna get 1 over meters here. And it's not gonna be dimensionless. What should we do?
We add the distance that we're taking the moment from the leading edge, or multiply.
But that is going to change based on your location, right? That's it. You multiply by chord length. Chord length is a length scale that doesn't change after you have set up your problem. Okay, so let me ask you this. What about pressure coefficient? I think we talked about pressure coefficient specifically in the previous. The problem is I'm teaching aerodynamics this semester as well, so I confuse the material I cover in this course and that course. So, but now don't go back. I want you to think and give me a formula.
Pressure over
That's it, right? Exactly. But the thing is, we usually deal with the pressure differential, right? How different is this pressure from the P infinity? That's this delta P is the thing determining factor, is an important factor for us in this type of analysis. Okay, so we are reminded of lift coefficient, drag coefficients, and the force coefficient, moment coefficient, all of those things. One thing that is going to be important for us, we are entering the flight mechanics part of the thing. So we are not going to deal with the like pressure distributions and all of those things that much anymore. We are only going to deal with the like flight parameters. So one thing that is very important when you want to identify the performance of an airfoil or whatever, like wing or an aircraft, is lift coefficient versus angle of attack. Okay. And we also have another one that is the lift coefficient versus the drag coefficient or the drag polar. So two main plots, CL versus alpha and the drag polar. And for those of you who have had Aerospace Lab 1 with me, you have actually done extensive analysis on this, right? Pardon me? Yeah. Yeah. So you know them by heart. You know the plots. You know the figures. You know the importance of them, and you know how they vary with different aircraft, different speeds, and everything else. Okay. But what we're going to focus on here is essentially how this acts for different airfoils. Let's do a symmetrical airfoil first. What is a symmetrical? What is the definition of a symmetrical airfoil? That's it. So essentially the camber of the airfoil, which is the difference between the mean camber line and your chord line, is zero, right? That's the idea. So for a symmetric airfoil, what's going to happen is here at angle of attack 0, you're going to get 0 lift coefficient, mainly because the streamlines are symmetrically, essentially the same, right? The distribution of the flow is very symmetrical over the chord length, right? So there is no pressure difference between the bottom and top of the airfoil. So you're going to get 0 lift, right? And this lift changes linearly until some point, and then we're going to have the stall condition at which we will see huge reduction in lift coefficient, right? Hopefully we are all familiar with the stall condition and what happens during a stall from aerodynamics. If you haven't passed aerodynamics, you will see more about this in your aerodynamics. But then the question is, what is going to happen if you are dealing with a cambered airfoil? A cambered airfoil looks something like this, right? What is going to happen to this line if you are dealing with a cambered airfoil? Pardon me? Pardon? I didn't understand the question.
It'll start higher.
It will start higher, or it will move to the left, right? So essentially, what Lawson is telling us is that because of the fact that there is some camber here, the streamlines on the bottom that's flowing on the bottom of the airfoil are going to be always applying more pressure than the top, right? So we can actually get the 0 lift at a negative angle of attack. And this is what you're going to see with a cambered airfoil. Okay? But this is true for a positive camber, though. What will happen if we were dealing with a negative camber? We shift to the right. So essentially, a negative camber would look something like this. We don't really deal with negative cambers, but there are, negative camber aircraft are not, we don't produce negative camber wings, but when you roll the aircraft 180 degrees and continue flying in this like rolled position, you are essentially dealing with a negative cambered airfoil. Yes?
If
Yeah, I mean, not in aircrafts though. Yeah. But the point is, the only difference it's going to make is that you are going to move to the right. The stall condition is going to happen. And is there any questions so far? So we are going to, if there's no questions, we are going to move on to some like analysis on these. I'm going to give you some equations on how to calculate the lift coefficient from pressure coefficient. And then we'll do some analysis that you haven't done in your fluid mechanics. The idea is here that, and we have talked about this many, many times, we have tried to hammer this concept that the only two ways a flow can exert force on an object is by shear stress and pressure, right? So the lift coefficient, drag coefficient, whatever, or forces, lift and drag forces and normal and axial forces are a function of, or have to be a function of pressure and shear stress. But in our analysis, because we are dealing with low speed aerodynamics, what is the main assumption we make here? What is one of the main assumptions we make here? Think about it. And we talked about this assumption in chapter 4 in detail. Frictionless, right? So and this is the same assumption we are going to make in this analysis. We are assuming the flow is frictionless or inviscid. This assumption can be true in many ranges of flow, low speed, high speed, in many ranges of the flow. The only problem that we are going to face with making this assumption is that we are going to lose the ability to calculate the friction drag, and the pressure drag calculations are going to be very inaccurate, right? Okay. So with this, essentially means your forces are only a function of your pressure. Pressure is going to change at each point of your airfoil. So we have, or pressure in general, or stress in general, is essentially a point force, right? A force that is being applied to a point, force per unit area, only applied to a point. Okay, so how can we relate this pressure to the force? What should we do? Pressure is being applied to a point. A force is applied to a area. And we want to use this pressure to find the force. Let's say we want to find the normal force first, normal and axial force, and then relate it back to your, or let's say we want to find the R, the resultant force. How should we relate this pressure to a force that's being applied to a point? Okay. Yeah. Why was it so complex? You have to take the integral, right? Essentially, we have newtons. We have newtons per meter squared, right? We have to multiply this by area. But since the pressure is changing at each location, at each point, we have to take the integral for, let's do for R first. Take the integral from leading edge to trailing edge. The upper P of the upper surface, ds, that's the element of your surface, minus P of the lower surface, ds. So the resultant force is essentially the integral of forces, the integral of pressure on the lower surface minus the integral of pressure on the upper. This is actually the other way around. Did I just PL minus PU. Okay. But if you want to find the force in the normal direction, we essentially have to find the normal component of that pressure. Okay. So let's say this pressure is always normal to your surface, right? But the surface here is making an angle with your chord length, right? Let's say, yeah, let's have a line parallel to your chord length. This angle is called theta, right? Let's actually call this angle theta. So P double minus. Does this make sense? Okay, so this is going to be your normal force, the direction of the normal force, but this is the direction of pressure. So one component of pressure is contributing to your normal force. The other component is contributing to the actual force. Is this clear? Okay. What is the component that is contributing to normal force? It's P cosine of theta.
Is that the same functionally as lift? Like, can we think of it as like the same thing? Because you said it was cosine theta, and there we start in cosine alpha.
That's a good question, and that's a very reasonable confusion that may happen. Let's actually try to look at a cleaner airfoil. Let's say this is your flow direction, means that this is your alpha angle of attack, right? And we are dealing with normal and actual force at this point. Okay. The idea is pressure is normal to the surface, right? We haven't talked about the direction of flow at all, right? And the surface makes an angle with your chord, right? Does it make sense? Or the direction normal. This is a geometric angle. It doesn't have anything to do with the flow direction, right? And this is essentially, you can calculate this from your design. This is something that you assign, right? You have the relationship between, you should be able to calculate this theta based on the curvature and each part of the airfoil. Right? For example, for a flat plate, what is theta here? 0, right? Because these two are going to be in the same direction. So hopefully that is clear. So your N is going to be equal to PL cosine of theta, which is not the angle of attack again, and PU cosine of theta again. Okay. And since we are dealing with airfoils, we are only dealing with a two-dimensional thing. So your ds is essentially going to be a small element on the surface, okay, multiplied by the depth. Two-dimensional. Okay, I think. So this is a wing, right? When you are dealing with the force, you are dealing with a three-dimensional wing, right? A small element in the integral is being, so ds, d of this area, it is a small element of area. When we are dealing with a two-dimensional analysis, we are assuming that the depth is 1. We have unit depth, right? So this small element of area is going to be this multiplied by 1. Does that make sense? Okay. So, and that a small element, a small length element, I'm going to call it a small s multiplied by 1. Again, a small s multiplied by 1. This 1 is a dimensioned parameter, 1 meter, right? Unit length, right? You can take the 1 to the other side and calculate force per unit length instead. Does this make sense? Hopefully. Yes. Okay, good. Okay, so then we can use the definitions we're going to have for, let's see, you can use the definitions we have for force coefficients and pressure coefficient and all of those things, and relate these to your pressure. But before doing so, we're going to make some assumptions that these are, we are dealing with thin airfoils. So how can we simplify that with that assumption? How can we simplify this equation with the assumption of thin airfoils? What is going to change here? Theta is going to be close to 0. So cosine of theta is going to be close to 1. Okay, so we can take the cosine and theta out, right? And then you divide everything by q infinity. S here, again, we are dealing with n prime unit per force per unit length, right? So your S here is going to become just your chord length multiplied by that unit depth, which is only the chord length, right? Okay, so if you divide everything by q infinity S, on this side, you're going to get C of n, force coefficient, and you're going to get P, and we are going to like subtract everything from P infinity as well. P infinity divided by Q infinity C, ds, thin airfoil, so we can just assume it is one-dimensional. And Pu minus P infinity divided by Q infinity C dx, right? So this ds, right, this small element on the surface became dx because it's a thin airfoil. So we are assuming it's just one-dimensional thing. Does this make sense? Okay. C doesn't change, so we can take it out. And delta P over Q is pressure coefficient. So your Cn is going to be equal to 1 over C integral of leading edge to trailing edge P CPL minus CPU dx. So if you have the pressure coefficient, the distribution of the pressure coefficient on the top and distribution of pressure coefficient at the bottom, you're going to get this. And since we are dealing with a thin airfoil, a two-dimensional airfoil, we can change the limits of integral to from 0 to C chord length. For what will happen, how can we calculate lift coefficient using this normal force coefficient for a small angles of attack? Exactly. So when you're dealing with a small angles of attack, normal coefficient and lift coefficient, normal force and lift force are essentially going to be the same. Same is true for axial force and drag force. So lift coefficient is going to be 1 over C, 0 to C, CPL minus CPU dx. Chord length, yeah. Whenever you see a C that doesn't have a subscript or superscript, is just referring to the chord length. Okay, unless I specify. Okay, so we should be able to calculate this lift coefficient for an airfoil, thin airfoil, for without friction, for a case without friction. Well, what does it mean? Let's say we want to have the distribution of pressure coefficient over your airfoil. We have two, and we actually, for pressure coefficient, we usually go from positive to negative. What does a positive pressure coefficient mean?
Your pressure is larger than your
To infinity, we have talked about this. And a negative CP is essentially telling us your pressure is smaller than P infinity. So on the upper surface, we usually get a negative value for your pressure coefficient. So the pressure coefficient is going to be pressure is going to be smaller than the pressure coefficient. But on the lower surface, it is usually not the case. So this is this type of distribution. What this equation is telling us is that to be able to find the lift coefficient, we have to find this area. So this is going to be your lift coefficient. So up until this point, we should have seen everything in aerodynamics. And if you don't remember, just make sure to ask why we didn't go into that much detail about anything. Okay. But what will happen to our formulation if we cannot assume the flow is incompressible? So what will happen to our case when the Mach number is larger than what? 0.3. So how should we find the lift coefficient? Because here we were assuming low speed, incompressible flow, a lot of assumptions we were making. Essentially, it's pretty simple. We just come up with a compressibility factor. Compressibility factor to correct or correction factor. Compressibility correction factor, which is essentially going to be the new CL is going to be CL and naught, which is your lowest speed lift coefficient. So this one, okay, divided by the square root of m infinity minus 1. 1 minus m infinity squared. That was my mistake. 1 minus m infinity squared. So low speed, this is your incompressible lift coefficient. And if you want to find the lift coefficient for Mach number that are larger than 0.3, you essentially make the incompressible assumption, calculate the coefficient, and then use this correction factor, which is 1 over the square root of 1 minus m infinity squared, to find the value for the compressible fluid flow. That's Mach number. Let's call it MA. Mach number. But what is the limitation of this correction? Mach number, I mean, if you go higher than 1, then, or 1, it is essentially going to be mathematically like it is what do you call it? Asymptote, right? It will be a mathematical asymptote. And larger than 1, you cannot have a negative value under the square root, right? Because we are not dealing with imaginary numbers. So let's have a distribution. So what is going to happen if you do this correction? What's going to happen is going to be this. Right? It will approach infinity as you increase the Mach number, your lift coefficient. Right? It will approach infinity. But at this, like let's say at these values and these regions, you are seeing a huge rise. So it's not just Mach numbers that have to be smaller than 1. It's also Mach numbers before this huge rise, right? Because after this, you're essentially introducing very unphysical corrections. So the limit for this correction, compressivity correction, to be true, and this is not just a random limitation. You can make some calculation and like find out that this compressivity factor's error becomes higher than like some percentage to come to this number. The same thing as we did for the Mach number 0.3, right? You remember that? Okay. Any questions so far? So let's talk about the critical Mach number and critical pressure coefficient a little bit. These parts are essentially the main part of the lecture today. For the most part, except for this compressibility correction, we have seen them before. Okay. The idea is when a flow is approaching your airfoil, or let me actually ask you, because I get a feeling that you are going to sleep little by little. We are getting bored. Just mathematics is sometimes boring. I get it. So, pardon me? Or I can ask you questions, right? Let's put the flames on you. Okay. So let's say we are at Mach numbers 0.3. What will happen to the velocity on the airfoil, on the upper surface of the airfoil, when let's say we are approaching it with the Mach number 0.3? You have to speak up. It will speed up. So it will be a value that is definitely larger than 0.3. Is it possible for it to be a sonic value or larger than that? Yes. Why not? Right? There's no limitation. That's correct. So we can actually find a Mach number at which you will get a sonic speed on your airfoil, a sonic region, inside which you're going to get m equals to 1. And that Mach number is called the critical Mach number. Okay? For that critical Mach number, okay, let me ask you this then. Where will you get the maximum speed, which means that the highest Mach number, right? The maximum speed is going to give you the highest Mach number. Where will you get this? Or what is the relationship between, or is there any relationship between the maximum speed and the pressure coefficient?
Would it be right after right after where the point the chord is the highest?
Chord is the highest.
The word is escaping.
The camber thickness is the highest.
Yeah. Like just getting like the top of like where it's the most distance from each other.
Okay, how does it? But how can you relate this to pressure coefficient? Like, what does it say about pressure coefficient? That is the question. How would you relate the maximum speed to the pressure? What is the relationship between maximum speed, the location at which you get the maximum speed, and the pressure coefficient at that location? Lowest pressure coefficient, right? Or the most negative pressure coefficient, which is the lowest pressure you're gonna. So this critical Mach number, okay, at which we're gonna get sonic speeds on the airfoil is going to give us another concept, another definition, which is the critical pressure coefficient. Pressure coefficient in general, the minimum pressure coefficient, is going to give us the Vmax or max Mach number on an airfoil, but the critical pressure coefficient is the pressure coefficient at which you're going to see a sonic Mach number at that specific location, right? If you are approaching your airfoil with the critical Mach number. Does that make sense? Okay, so how should we determine that? How should we find this critical Mach number and critical pressure coefficient? Let's actually have a figure with CP versus Mach number. How would you think the pressure coefficient change? How will it change? As we increase the Mach number. And this is the minimum pressure coefficient. And this side of the axis is going towards negative. So positive going to negative. How will this minimum change as you increase the Mach number? What will happen if you increase the Mach number? We are not in the supersonic yet. We are in subsonic. Velocity increases. What does it mean for pressure coefficient? It will decrease, which essentially on this curve, it will look something like this, right? Okay. So let's say this plot is for a thick airfoil. How would this change? How would this plot change if you are dealing with a thinner airfoil? Essentially, this shows the relationship between the pressure and velocity, right? The idea is as we increase the velocity, your pressure is going to decrease, right? That's the idea. So how can you, or how does it change? How does this relationship change when you decrease the thickness of your airfoil? Why would it shift downward?
I'm not sure whether it would shift upward or downward.
Okay.
The air has to move a smaller distance to get to the other part of the free stream, so it wouldn't have to move as fast.
Okay. Not flattened. Okay, what else? Near left, Igor. No idea. It will, yeah, it will definitely. Okay, think about the last one was moving in the correct direction. Nila, do you have anything? The question is, what will happen to this line when you decrease the thickness of your airfoil?
It's gonna be less than, and it's less than theta, cosine theta, and the other equation. So I believe the angle will be less steep.
So we are actually talking about the relationship between pressure and the Mach number. So that angle theta doesn't really play a huge role here, right? But think about it this way. Think about the perturbations. A thick airfoil is going to cause in a flow versus a thin airfoil. A perturbation a thin airfoil is going to cause is going to be less, right? Because it is thinner. So what you're going to get is going to move downwards, right? As I forgot your name. Yeah, Trey. Yeah, sorry. As Trey mentioned, and others tried to elaborate on that point. So that perturbation, we are essentially going to lose less momentum. Your pressure is going to increase, right? Or the pressure decreaser is going to be smaller. And we're actually going to have a critical Mach number line here, or critical CP line. This line identifies the critical pressure coefficient. These values are going to give you the critical Mach numbers for each airfoil. So what was the critical Mach number again? Was the Mach number at which you are going to get sonic speeds on your airfoil. What time is it? Today is a slow day, isn't it? Yeah, for some reason. So I feel for you. And I'm sorry that class is a little boring today, but I guess we have to power through. Okay, so let's see if we can find a relationship. I'm not going to drive the relationship. I'm just going to write them down. But it's essentially the derivation is inside the book, is in the book, and it shouldn't be that hard for you to follow the derivation. But if you wanted to, you can always ask me questions. Pressure coefficient, the minimum pressure coefficient for a Mach number is going to be equal to 2 over gamma and infinity squared, 1 plus 1/2, 1 minus gamma m infinity squared, divided by 1 plus 1/2, 1 minus gamma m squared. So this is using this equation, you actually should be able to find, and this is to the power gamma divided gamma minus 1 minus 1. Okay, using this, we can actually, we have found this relationship based on the isentropic relationships and all of those relationships we have seen before. So this is, this shouldn't be anything, there is nothing special in the derivation of this equation. But using this equation, you should be able to find the pressure coefficient at each location, as long as you know the Mach number at that specific location. So how can we find the critical pressure coefficient then, based on this? That's it, exactly. So the definition for critical pressure coefficient was the location at which you're going to get a local sonic velocity. So we are going to put Mach number equals to 1 here. and everything else is going to remain the same. Any questions so far? So how can we find the critical Mach number? We are essentially want to go about this the other way around, right? Here, using an M infinity, we found a critical pressure, right? So to go about it from the other way is that we have to find a minimum pressure on an airfoil, and then using that, we need to find the critical Mach number, right? So it's essentially, we're going to get the same equation. The only difference is that the goal of that equation is to find the Mach number instead of critical pressure. And let's say we have the minimum pressure, we calculate the minimum pressure using the incompressible analysis. So we have to include the incompressibility factor as well. If you recall, this was the, but everything else is this exactly the same. Okay, so are we all familiar with the, do we all understand the concept of critical Mach number and critical pressure? Yes or no? Yes. Okay, so let's actually stop here because there's no point in like continuing a lecture that's putting us to sleep. I'm going to sleep. So let's just stop here. Yeah. It is one of those days today. I have a lot of things to do actually. But let's just stop here. We are going to hopefully pick up the pace next lecture. And we are going to talk about drag divergence and induced drag and all of those fun stuff in the next lectures. The wave drag, all of those fun stuff in the next lectures. And for the rest of the class, if you want to leave, you can leave. If not, you can just sit here and chat, ask questions if you have any, or talk about anything other than politics. No. It's the exact same equation. The only difference is M critical. Yeah. Yeah. For this material, yes. Yeah. But the thing is, since this is essentially, especially if you want to calculate the critical Mach number, you have to do a lot of runs, or either write a code or whatever, right? You have to do something. So the equations and the concepts themselves are not that hard to deal with. It's just you have to make sure that you are not making any mistakes. So do you guys have any questions or concerns about the class, about your future, or tips for the homework? The homework is not that hard. The thing, I assume you have had harder questions in your aerodynamics. Yeah. How did you like your aerodynamics course? What did you learn in your aerodynamics? Yeah. Everyone has for aircraft.
And we did the homework, and I got stuck on this one problem for like 3-4 hours.
the Sutherland's law problem, and we hadn't learned about it yet. And he changed instead of U rep, it was like C2. So he changed like the variable, and he wanted us to like to look at the units and know that that was the constant that went there. And everybody got there and was like, how do you solve that problem? And he was like, I made that one intentionally confusing. And I started like laughing so
Okay. You started laughing. Okay. I assume it was a nervous laugh, like nervous, whatever they call it. It's hysteric laughs, right? Not from joy, not from enjoying yourself.
He's a hard professor, but he teaches well.
I enjoyed learning the material. It's just like after class where it kind of
Goes hard.
Yeah. Yeah, actually, for flight mechanics last year, I don't know what the other students, the previous year students have told you guys, but for flight mechanics last year, we had this midterm, which was hard, because they actually asked for it. I told them that having an in-class exam is going to be easier. Just sit there, solve it. They've had me for other classes, so they knew it, right? But they asked for a take-home test, and I gave them a very hard test. And I mean, I gave all of them 100 or 80 or 90. Like, I didn't grade the homework because it was a very long exam. I didn't want to grade it. I just gave them. So because it was an unfair exam, to be honest.
you know,
Just one of those days, right? Yeah.
For Ruth's final, we had a question where we had like 100 points of data that he wanted us to graph. I just didn't feel like doing it, and I did all the math for the rest of the exam. I got all the math right, and I was like, I don't think you'll count off too much if I don't include a graph because it's like 100 points. I want to graph all of it. He took off like 40 points. I got everything else right.
40 points. So you got a 60.
Yeah.
Wow.
I
Okay.
made the class and dropped my final grade down to like a C+.
Wow.
You have to use like MATLAB and X4 and all this other stuff.
Yeah.
And all the computational problems on top of it.
It's like 3 days.
Yeah. You needed all the days to do it.
I think that's how much time he gave us if we used it. He gave us 3 days. We used those 3 days.
Yeah, that's usually what happens. You have to take his propulsion class. I mean, you don't need to because it's a 700 level class. But if you end up being a master's of aerospace student here, you will take that class, and that class is just unbelievable. But the one I think I need to stop recording for this. I want to give you a tip. Okay, let me stop the live stream as well. Emery, could you change the title? It says Aerodynamics. I will change the title. I don't know if you're still here or not, but I will change the title. Okay, so